So once again, welcome to another lecture on rectifier. Rectifier, it is a circuit which is used to convert AC signal into DC, which is also represented as a pulsating DC. Now, first type that we have seen in last lecture. Now, in today's lecture, we have started with the another type of rectifier that is called as folio rectifier with center tap transformer. Means there are two types of folio rectifier. One it is with center tap transformer, and another one that is nothing but bridge rectifier. Now in this folio rectifier, the basic principle of center tap that should be used. Now this center tap transformer, it is whatever the signal which is appears across S1 and S2, they are having 180-degree phase difference between each other. Means if S1 it is said to be positive or positive, at the same time S2 should be negative, and these things are related with the center tap transformer, center tap. Okay, so the across the center tap transformer, the two terminals or the AC input it is applied at the primary side, and at the secondary side the two diodes are connected to the two secondary terminals of the center tap transformer. Okay, so during positive half cycle of AC input, what happens? Suppose S1 it is said to be positive, or positive half cycle should be appears across this S1 terminal or at the S1 terminal, and at S2 the negative signal or negative signal should be appears across D2, and hence diode D1 should be only forward biased for the positive half cycle of AC input. Okay, so as this diode D1, it is forward biased, the current it is allowed it to pass through this diode and through this load register and towards this center tap. Means this is the direction of current for the positive half cycle, that is S1 through this D1, through this RL, and through this center tap terminal, that is C. Now during negative half cycle of the AC input, what happens? The S1 it becomes negative, and S2 it becomes positive. That is, the signal appears across this S2, it becomes positive. As S2 it is positive, diode D2 should be forward biased, and at the same time diode D1 should be reverse biased. Now what happens? The signal should be current should be allowed it to pass through this diode D2 as it is in on condition. Diode current should be flows like this through this diode D2. Now here it has direction towards D1 also, but as it is in reverse bias condition, no current it is allowed it to pass through this diode D2. Only the path it is through this load resistor and towards this center tap. Means here in this way the current which is flowing through this load resistor RL having only one direction, that is unidirectional current, should be allowed it to pass through this RL. Means it is from this top side towards this bottom side, that is from this terminal to this terminal. That is the current direction for this folio rectifier. Now here what happens? For both positive half cycle, there is conductivity should be observed. Means for first positive half cycle of AC input, diode D1 should be forward biased. Then for another half cycle, that is negative half cycle of AC input, the S2 it is said to be forward biased, and therefore at the type diode D2 it is forward biased, and therefore current should be allowed it to pass for both positive cycle as well as negative half cycle, and the direction of current it is pulsating but having only one direction, and the direction it is represented in this figure. So also we have to see the waveform, that is not only across S1 and S2, because these are 180-degree phase shift. I have to represent only the AC input and the output which is to be observed. Now here the AC input it is appears. Now this AC input it is represented as AC cycle, which is having the radian angle value, that is pi, 2 pi, 3 pi, 4 pi, like this. Now here the output voltage we have to represent it here. Now what is the input voltage? Peak voltage. That peak voltage value it is represented as a Vm. Means here it is positive Vm. At this side also there is Vm. Now if you want to measure the voltage between peak to peak, it becomes twice Vm. म्हणजे जर if you want to measure from this point up to this point, the total peak to peak voltage, it becomes twice Vm. Now during positive half cycle of AC input, what happens? Diode D1 should be followed by the, means diode D1 should be becomes on. Means here I have write that is diode D1 should be becomes on. Means for 0 to pi angle, the diode should be D1 should be followed by the, and D2 should be reverse biased. Therefore, there is no current flowing through this diode D2. Only diode D1 should be conducting, and here because of the diode D1, the voltage must be appears across the load resistor. It is represented like this. For the next half cycle, what happens? For the next negative half cycle of AC input, the S2, it becomes followed by the diode D2, positive. Diode D2 should be followed by this, which is allowed to pass the current, and hence diode D2 should be becomes on for this cycle. Means from pi to 2 pi, the diode D2 should be becomes on, and for 0 to pi, diode D1 should be becomes on, and this cycle should be goes on continuously. That is here again diode D1 becomes on for next half cycle, and for then D2, means this successive method, successive conduction for each cycle, that should be made for positive half cycle as well as negative half cycle. Okay, so I think that you can understand the diagram as well as input output waveform for this case. Now we have to derive some mathematical formulae for this case also, and these are represented like this. First thing, it is that the average or DC voltage. Now average or DC voltage, it is we have to observe for this case. Means how much amount of DC contents are present within this waveform. That we have to calculate with the help of this average or DC voltage. Now here the curvature nature should be there. As there is curvature nature, we have to take the integration form, and we have to consider one cycle, that is 0 to pi, that is here from this stage start point to up to this. Means for one cycle, how much amount of output should be appears, that is average or DC voltage because of diode D1 and D2, that we have to find. Now here the formula, it is represented as VDC equal to 1 upon 2 pi into bracket, because this is we have to consider for one cycle. Okay, so into square bracket, into bracket, what happens? 0 to pi integration Vm sin omega t d omega t, plus another integration from pi to 2 pi Vm sin omega t minus pi d omega t. Because for positive half cycle, there is one diode conduct. For negative half cycle, the another diode conduct, and the angle value should be also represented as omega t minus pi. It is not only the again omega t, but here we have to represent, because it can conduct only for half cycle, and therefore we have to represent like this. Now, if we want to solve this, the in last condition, that is for half wave rectifier, we have to solve the formula for 1 upon 2 pi Vm integration from 0 to pi sin omega t d omega t. For this case, we have to find out that values. Now here, that value should be again added, that is Vm pi to 2 pi integration from pi to 2 pi sin of omega t minus pi d omega t. Now, if we want to solve this condition, we have to get the equation, that is VDC equal to Vm upon 2 pi. Now, here we have to obtain this sin omega t integration, and by putting the upper limit and lower limit, we can get the value 2. For this case also, we have to get the another value, that is 2, and therefore Vm upon 2 pi into 4, and that is 4 Vm upon 2 pi, and here we have to represent that value as a VDC equal to twice Vm upon pi. Means this is the simplified value for the full wave rectifier with center gap transformer. Okay, so another thing, that is RMS quantity, that is RMS voltage. VRMS, it is again calculated here. VRMS equal to into square bracket, that is square root should be there, that is here 0 to pi Vm square sin square omega t plus pi to 2 pi, integration from pi to 2 pi Vm square sin square omega t minus pi d omega t upon 2 pi. Now if again by putting the values for the sin square, again for the sin square, that is 1 minus cos 2 omega t upon 2, means by using this formula we have to simplify. That simplification, if you want to make that one page should be fulfilled, and therefore to minimize that condition we have to simply put the formula and representing the direct output. That output should be represented as the Vrms equal to Vm upon square root 2. Now this value it is obtained from this case. Now the DC current IDC, it is calculated as VDC upon RL. By putting the value of VDC from above equation, we have to represent that is twice Vm upon pi into RL. Now again we have to simplify this equation as IDC equal to twice Im by pi. And similarly, again we have to find out the RMS current, and RMS current it is calculated or by using that Vrms formula that is here. We have to directly represent this formula as IRMS equal to Im upon root 2. Now where the value of peak current or Im, it is represented as a Vm upon RL. Means for both cases, for half wave or full wave, the value of peak current it is represented as a Vm upon RL. Now we have to find out the another condition for this case, that is the values for the efficiency of the circuit. Now the efficiency of the circuit, it is represented like this. That is, it is the ratio of our average power delivered to the load divided by AC input power given to the circuit. Now here it is that eta equal to PDC divided by PAC. Now DC power, it is nothing but I square R, or AC power, it is also the RMS I square R, but the values of current, it is IDC square into RL upon IRMS square into RL. That is for DC power and AC power, we have to represent this value in terms of IDC and IRMS. So here by putting the value of IDC and IRMS, that is IDC equal to twice Im by pi its square into RL upon Im upon root 2 its bracket square into RL. Means if we want to simplify this value of efficiency, that is the RL value should be cancelled, peak value should be also cancelled, and remaining term should be 8 upon pi square. Means we have to simplify this form 2 pi and the square root 2. We have to simplify this case and we can get the efficiency of the circuit. It is nothing but 0.8114. That is nothing but, if we want to calculate the value in terms of percentage, it is 81.14. Now efficiency of the low half wave rectifier, it is very small, and here the efficiency value should be increased. Means the efficiency for the half wave rectifier, its value should be approximately 40%, 40.6%, but here the value should be increased up to the 81.14%. Means that efficiency value should be increased for this case. Now next thing that we have to measure, that is nothing but ripple factor. Now here I have to directly represent the formula, that is I have not given that ripple factor. It is the ratio of the RMS quantity present at the output divided by DC quantity. Instead of representing that formula, I have to simplify that formula and representing that formula like that. Ripple factor, it is equal to square root IRMS upon IDC bracket square minus 1. And this term, all terms should be under square root. Means here, this term, it is not the outside the bracket. Okay. So again, by putting the value of IRMS and IDC here in this equation, we have to simplify this. That is Im upon root 2 and twice Im upon pi. By putting that value of IRMS and IDC, we have to make the simplification, and after making the simplification, it is represented like this. Now again, if you want to get the values, that value should be represented like this. That is ripple factor for full wave rectifier with center tap transformer. It is nothing but 0.482. That is 0.48482. Means its value should be also smaller. That is the very small value for this case. Now the next thing that is AC component which is present at the output side, it is very smaller. Now again in that waveform we have to see it. Now before going to that waveform, we have to see the another term that is nothing but peak inverse voltage. Very important term, because whenever the diode must be operate in the proper way, we must have to represent that how much amount of reverse voltage must be applied to that diode in that reverse bias condition. And for that purpose, we have to find out the value for PI. Now here, the PIV value is directly I have to represent as a twice wave. How it appears? How it appears if you want to see that values for this case, now I have to simply draw the diagram again. Here it is the diode D1 and here diode D2. Here it is the center gap. Now here what happens during positive half cycle, we have to say that the S1 it is positive. And S2, what about S2? S2 it is negative, means here the positive voltage should be Vm, negative voltage should be also Vm. That peak voltage value should be Vm. Now this voltage, these are connected to each other. Then it is given to the load resistor. Okay. So diode D1 should be forward biased for positive half cycle, and diode D2 should be reverse biased. Now, when the diode D2 it is in reverse bias condition, how much amount of voltage should be appears across this diode? That is nothing but PI. Now here, this positive voltage should be appears here also. That is maximum voltage should be Vm. And at the side, the negative value means here it is minus Vm and here it is plus Vm. And therefore, if you want to make the summation of these two quantities, that is, it becomes total twice Vm. Means when the diode it is in reverse bias condition, either for D1 or D2, for both cases, when that diode it is goes into reverse bias condition, at that time its reverse voltage should be becomes as a twice Vm. Means this diode has capability to sustain that voltage which is applied. Now the value of ripple factor in this output condition, that we have to see. Suppose the output it is like this. Here it is the output. Now how much amount of AC content should be there? Here it is the AC content. म्हणजे ह्या ठिकाणी जर आपण बघितलं तर AC content हे एवढंच असणार. And therefore the value of ripple factor for full wave rectifier it is smaller, and this rectifier has one drawback, that is its peak inverse voltage should be smaller. That is the only one drawback. Other are advantages as compared to half wave rectifier. Okay, thank you. We have to see another bridge rectifier in the next lecture.